In this lecture, we're going to talk about polynomial functions that are compositions of power functions. So let's take a look here. Polynomial function is a bunch of terms connected by a plus, or if the coefficients are negative, a minus, of power functions from some degree n all the way down to the constant. So for example, things like x squared plus 3x minus 7 is a polynomial, and the degree of it is the highest degree that is present. The graphs of all the polynomials are smooth curves. So there's no jagged corners, there's no weird holes in the middle. All the graphs are going to be smooth curves. And the nice thing is, because they're composed of the power functions as their building blocks, we can use the dominating power analysis to actually produce pretty good sketches of these polynomials. So let's take a look at our first example here. X cubed minus 4x. As before, we're going to think about the behavior for small values of x and the behavior for large values of x. Remember that for small values of x, the small power dominates. Here I have two terms to pick from, x cubed and 4x with a negative in front of it. So this comes as one term, and x cubed comes as its own term. Between these two terms, one has the higher power than the other, so they will differ in the regions of x that they dominate. So for small powers of x, the small power will dominate, which means that for small values of x, the function will look like minus 4x. So this is going to happen near the origin. For large values of x, we're going to see the larger power dominate. So this is what the function is going to look like for large values of x. So let's start a preliminary sketch of these ideas. So what I have is, near the origin, the function looks like minus 4x. What does minus 4x look like? It's a line with a negative slope. So near the origin, I have a line of negative slope going through the origin. Let's make it clear that it's linear. Okay, something like this. For large values of x, I have x cubed. So overall, x cubed looks like this snaky shape, as is, right? However, I'm only interested in this snaky shape for large values of x. So I'm only interested in the pieces that are at the ends of it, not near the origin, at the large positive and large negative values. So these are going to be pieces that remain from my x squared portion of the analysis. Now, I can already likely see what the overall shape of this function will look like by simply realizing that I need to connect all of these three pieces in some smooth, continuous kind of way. So I'd likely start here, go up here in order to be able to follow the line, and then have to cross back out in order to join my end behavior on the other side. In order to be a little bit more precise, we can also find specific points that belong to these graphs. In particular, we can look for X-intercepts to see where the function intersects the x-axis so that I know whether or not it actually does, and if it does, then at which points it actually happens. So for the x-intercepts, these are points where the graph intersects the x-axis, which means that the vertical component of it is equal to 0. So we're going to set y to be 0 and then solve. If y is equal to 0, we have this equation to work out. So I'm going to have x cubed minus 4x is equal to 0. And then again, remember, don't divide, factor. I can factor out x. What I'm going to have left is x squared minus 4. And now that I have two factors, once again, in order for them to multiply to be 0, it means one of them has to equal to 0. So either x is 0 or x squared minus 4 is 0. So that means x squared is equal to 4, which means that x is equal to plus or minus 2. So overall, I have these three intercepts to put on my graph. X equals 0, which is the origin, so my graph already goes through the 0 there, which is good news. Positive 2 and negative 2, as dictated to me by the solution to my equation. And now I have everything that I need to actually complete the picture. So my graph will start off with the with the x cubed behavior over here, will go through the intercept of -2, back along the -4x line near the origin, up through the intercept of 2, and to join the large value behavior at the other end. Okay, so overall, my graph is then going to be from here through the intercept, along the line, through the intercept, and joining the end behavior. Okay, notice, of course, that I don't have to be precisely on the actual sketches that I started. These were just qualitative behaviors. So as long as I am generally following the spirit of the actual behavior, I am in good shape. Okay, let's take a quick look at a couple of fast checks to make sure that we understand the concepts properly. This and the next slide have 2 multiple choice questions. So I suggest you pause the video here and try to actually address these questions on your own before coming back to discuss how to solve them. Okay, so here we have a graph of a function x to the 5th minus x squared. So again, polynomial, it's going to be a composition of the 2, in this case, power functions that are x to the 5th and minus x squared. The large power is going to dominate for large values of x, and the small power is going to dominate for small values of x, or near origin values. So that means that whatever graph corresponds to this function has to look like minus x squared near the origin, which means that it's a downward facing parabola, and it has to look like x to the 5th for large values of x. So overall, x to the 5th is a snaky shape. But here I'm only interested in the shape for large values of x, so I'm only interested at the sort of ends of this snaky picture. So it's going to have the beginning and the end of the snaky picture, and near the origin it has to look like a downward facing parabola. The only graph that satisfies this particular behavior is graph B. For the second part here, I have something of the exact same spirit. So again, if you haven't done so yet, pause the video so you can try this out for yourself before I tell you the answer. So my graph here, or my function here, again, 2 pieces, x to the 5th for large values of x, and minus x cubed for small values of x. So that means that near the origin, my graph has to look like negative x cubed. Now, this is why the sign is important, because it will really affect the behavior. X cubed looks like this. Negative x cubed looks like this. So that means that my function near the origin has to look like that. For large values of x, it looks like x to the 5th, which means that it has a snaky shape, but I only care about that at the ends of the snake. So overall, I'm going to have x to the 5th at the ends and minus x cubed near the origin. And the only function that satisfies those behaviors is the function in part A. Let's take it one step further and actually sketch these functions ourselves. You already have all the tools that are necessary for this to complete this exercise, so I encourage you to pause the video and actually try this out for yourself. So here we have 2x cubed minus 4x squared. Again, the dominating power analysis suggests that I have 2 pieces to this function. The larger power, which will dominate for large values of x, and the smaller power that will dominate near the origin, or small values of x. So even with this very basic information already, I can start sketching what my function will look like. So near the origin, it looks like negative 4x squared. Negative means I have to do something to my graph, and this is a parabola. So the negative means I have to face my parabola down. So it's a downward looking parabola here. And for large values of x, it looks like 2x cubed. Positive number, so the regular x cubed is going to look like that, but I'm only interested in the ends of it for large values of x. So I'm going to take the 2 pieces at the end of each of the snaky portions. Okay, so this is where I'm at, and now I have to somehow connect these two pieces. So it's pretty clear that I can actually just connect them like this. However, if I want more precise information, then I can look for intercepts and see if I can get those narrowed down and therefore have a little bit more of a concrete sense of where this function crosses the x-axis. So let's look for x-intercepts. So for x-intercepts, once again, we set y to be 0. So I'm looking at 2x cubed minus 4x squared to be 0. I can factor out 2x squared here. So what am I going to have left? X minus 2 is equal to 0. And as before, either the first part is 0, which gives me the origin, or the second part is 0, which gives me x equals 2. So I know that this function will cross at 0, and this function will cross at 2. So now I can see that there is really only one way to connect all of these pieces together. I will start down here. I will follow the parabolic behavior near the origin. I have to turn around to go through the 2 and go back up to join the other side of the large values of x behavior. And this is the graph. You can pull up the Desmos and make sure that this graph actually corresponds to what the graphing calculator will tell you. But I'm pretty certain with such simple graphs that we have it right. Let's take a look at the next one. Again, if you haven't yet had an opportunity to pause the video, I strongly recommend you do it now so that you can practice doing this on your own. It is one thing to watch me do it over and over again. It is completely different to try this for yourself. So what I have is this polynomial has 3 terms. So what I'm actually looking for, as before, is the largest power that will dominate for large values of x. So here powers of x are 6, 2, and 3. So the largest one, of course, is x to the 6. So this will dominate for large values of x. The smallest power is minus x cubed. I just realized I have a typo. This should be a 4th to have the graph that I have in mind. So this is where we're looking at for small values of x. Okay? Everything in the middle doesn't matter. I'm only looking at the largest and the smallest powers for dominating power analysis. Okay? This is key here. In fact, I encourage you to actually do the example with my typoed graph of 2x squared and see how that changes the analysis. So for large values of x, I have x to the 6th. X to the 6th is an even power, which means that I'm looking at a parabola, but I'm only interested in it for large values of x. So I'm only interested at the beginning and the end values of it. In the near the origin, my graph will look like minus x cubed. So once again, if I have a snaky parabola, snaky shape for x cubed, then minus x cubed is going to be the same snaky shape, but in the opposite direction. So I'm looking for here is something like this near the origin. Okay, so this already tells me that I am probably in pretty good shape with what I have so far. If I have to connect everything by a smooth curve, I have an idea of what the overall shape of the graph will look like. But if we wanted to take it further, we could try to solve this equation to identify the x-intercepts. Unfortunately, the higher degree equations are more difficult to solve, so you can try to set it up and see how far you're going to get. But in this particular case, I am going to settle with what I have so far for the behavior of the function and connect the corresponding pieces of my analysis so far. Okay, once again, I encourage you to actually go through this example with the square on the other term to see how that graph will differ from this one, how the change in one exponent will actually affect the change in the overall picture of the graph. Next up, we're going to talk about rational functions and in particular Hill functions. So rational functions are yet another way of putting power functions and polynomial functions together. So far, within the polynomial functions, we see addition, subtraction, multiplication. Rational functions are a way to introduce division. So a rational function, a ratio, is in fact a ratio of two polynomials. The top is a polynomial, the bottom is a polynomial, and the only thing that we're not allowed to do is divide by 0 as usual. So some examples of rational functions are something like, let's say, 2x to the 4th minus 7x squared plus 3, whatever polynomial you want, divided by whatever polynomial you want. So here, the key though is that of course the polynomial on the bottom cannot be 0. It could be 0 for some values of x, it just cannot actually itself be 0. So polynomial function over polynomial function, and your functions are allowed to be as difficult or as easy as you want them to be. One particular type of a rational function that we're going to work with quite a bit is so-called Hill function, which has the following form. It's a constant a and a constant b, and some power of x present in the term on the top and the term on the bottom. So let's take a look at the overall terms. Ax to the n, b plus x to the n. So on top I only have one term, on the bottom I have a constant and a second term. But the power on both the x's is the same. So for some examples of Hill functions, here we go like 5x divided by 7 plus x. So both x's are to power 1, so this is power 1 Hill function. Or we could have 5x squared over 7 plus x squared. This is going to be a power 2 Hill function. Again, notice that my constants can be anything, but my powers have to be the same on top and bottom. So you can take that to any power with any constant and produce a Hill function. Because these functions are going to arise in a variety of applications, we're going to focus on considering them for x greater or equal than 0, because x will stand for a value of something that cannot itself be negative, such as a concentration of a chemical or some kind of value that will only make sense biologically if it is positive. The Hill functions are named after Archibald Hill, which was a British physiologist that studied biophysics and operational research. He, in fact, won a 1922 Nobel Prize in Physiology and Medicine for his work on how muscles actually work mechanically. These functions are going to be useful in a variety of ways. So first, we're going to have an example and think about how we can sketch this function using the already developed power analysis of ours. So what I have here is a Hill function because on top I have one term, on the bottom I have two terms, one a constant, one a power, and the power of x is the same on both top and bottom. So what I'm going to do is, as per my dominating power analysis, I am going to analyze this function for small values of x, and then I'm going to analyze it for large values of x using the dominating power analysis on the top and the bottom separately. So let me rewrite this function here. So f of x is equal to 5x squared over 1 plus x squared. And now let's think about what happens for small values of x. Now on top I only have one term, so there's nothing I can do here. I am stuck with this term on the top, no matter what x is. But on the bottom, I have two terms, 1 and x squared. Now, the key here is to realize that this one can actually be thought of as x to power 0, which rewritten as a power of x makes it easier to see the comparison between the two powers. So remember that for small values of x, small powers of x dominate. So between x to power 0 and x squared, x to power 0 is the smaller power of x, so it will dominate the denominator. So I can essentially ignore this second term that's not going to give as much weight to the polynomial for small values of x, and what I will have at the bottom here is just this remaining 1. So just to rewrite this as a more reasonable format, 5x squared. So this is what happens for small values of x. What happens for large values of x? Well, I'm going to start off with the exact same formula. After all, I have the exact same function. But now I have to think of the dominating power analysis in terms of large values of x. Again, on top, I have no choices. I am stuck with 5x squared no matter what, because I only have the one term to work with. But on the bottom, I still have two terms, and for large values of x, it's going to be the larger power that dominates, which means that I can safely ignore the smaller power and say that my function for large values of x on the denominator here will look like x squared. It makes a little bit more sense intuitively for large values of x. Think about this term on the bottom, 1 plus x squared, and think about what if x is a very large number, like a million. A million squared is a huge number. So adding this constant to a million squared is not even a drop in a bucket. It's basically nothing. That's why for large values of x, it's the biggest power that will outweigh all the other components, and therefore in the approximation way, that's the only one that we're going to keep. Now the good thing here now is I can see that I can actually just cancel x squared on top and the bottom out, and what I end up with is just 5. So now once I have this figured out, let's draw the picture of what I have so far. Again, remember that these functions are going to be mainly considered for positive values of x, so I'm going to focus on creating a graph in the first quadrant here, so only for positive x's. So near the origin, I have that my graph looks like 5x squared. So a parabola looking up near the origin here. Okay, there we go, a little parabolic shape. For large values of x, my graph is going to look like 5. This is a little tricky because it's kind of very, very simple. So let's think about what that is. F of x, which is y, is going to equal to 5. What does y equal 5 look like as a graph? Y is my vertical axis here. So y equals 5 is going to be some point on the vertical axis here, right there. Y equals 5 is in fact this horizontal line. So what that means is for large values of x, my graph looks like a horizontal line at 5. So for large values of x, my graph will literally look like this line right here. Okay, so now connecting the two things together, near the origin, my graph is parabolic, and for large values of x, it approaches this line of y equals 5. Okay, let's maybe label this. This looks like 5x squared, and this looks like 5. And there we have the first graph of a hill function that has degree 2. I'm going to leave this second example for you to sketch out the cubic hill function in the exact same way as on the previous slide. Analyze the behavior for small values of x, analyze the behavior for large values of x, and produce the graph that combines both of those behaviors on both ends of the function. So for the dominating power analysis, we will have two cases. We will have to consider what happens for small values of x, and we will have to consider what happens for large values of x. Once we have those two cases analyzed, we can actually put our analysis on the graph. So for small values of x, I'm going to start with my function. I'm going to rewrite it as is, just so I can look at it a little bit more closely in detail. Remember that for small values of x, small powers dominate. And I'm going to analyze the two polynomials involved in building this function separately. On top, I don't have a choice. There's only one term. So no matter whether it's small values of x or large values of x, I don't have anything to pick from. So I have to stick to the term that I have. So this will remain as is. On the bottom, however, I have two terms, a constant and a cubic term. And I have to figure out which one of these will dominate for small values of x. It's important to notice here that this 7 can actually be thought of as 7x to power 0, because anything to power 0 is simply 1. So between these two terms now, we know that the smallest power will dominate for small values of x, which means that for small values of x, it's going to be 7 that dominates this entire denominator, and I can think about essentially ignoring the x cubed for now. So overall, for small values of x, my function f of x is going to be approximately equal to whatever was on the top divided by 7. It's probably easier on the eyes if we rewrite this last term as a constant, which is 2/7 times the power function, which is x cubed. Similarly, we're going to think about what happens to this f of x for large values of x. So once again, let me just rewrite the function. So I have 2x cubed over 7 plus x cubed. And as before, I'm going to analyze the top and the bottom separately. On the top, I only have one term. There's nothing I can choose between, so I'm stuck with whatever I have on top as given. On the bottom, however, I have two different terms, and I have to decide which one of them dominates for large values of x. As I've already noted here, the 7 corresponds to x to the 0th power, and we know that for large values of x, it's going to be the large powers of x that dominate, which means that x cubed will dominate this entire polynomial. So I can think of 7 as not really making a difference. This is actually really easy to see in terms of large numbers. If I, for example, plug in 1,000,000 into x, it's going to be 1,000,000 cubed, which is a huge number. Adding a 7 into it is like a drop in a bucket. You won't be able to notice that. This term is going to take over this entire polynomial. This term is going to be the one that matters for large values of x. So that's the term I'm going to rewrite, I'm going to keep as dominating for large values of x. So I have 2x cubed over x cubed. And I notice, of course, that now that I have that, I have x cubed on top and bottom, so they can simply cancel out, and I will get just a 2 as the answer here. So for small values of x, my function behaves like a constant times a cubic, and for large values of x, my function behaves like a constant, 2. I could start drawing already, and I could also find x and y intercepts of the function. Let me start on the graph and then make it more precise by actually computing the intercepts to make sure that I have everything set up properly. Once again, notice that for Hill functions, we'll only be drawing them for x is greater or equal than 0, simply because the applications that we're interested in will only make sense for positive values of x. So in order to find the x-intercept, I'm going to set y to be 0. My y is equal to this function right here. So what I have is 2x cubed over 7 plus x cubed is equal to 0. So now let's take a look at this. What I am looking at is I have a fraction equal to 0. The only way that I ever have two numbers divided by each other producing a 0 is if the top is 0, okay? A fraction is only ever 0 if the top of it is 0. Now I can divide both sides by 2, take cube roots, and notice that the only solution to this equation is going to be x equals 0. In order to compute y-intercepts, I am going to set x to be 0. That's the easier procedure because I literally plug in 0 everywhere in here. So what am I going to get? Y is equal to 2 times 0 cubed divided by 7 plus 0 cubed. I have 0 divided by 7, which of course is just 0. So my only intercept is x equals 0 and y equals 0, which is the origin itself. That's the only time the graph actually crosses any of the two axes. Now let's put together all the information that we have. For small values of x, my graph looks like a positive cubic function. So what I have is a snaky behavior near the origin. For large values of x, it looks like a constant 2. Note that this corresponds to y values. Y equals to 2 is a horizontal line at 2. So I have myself a horizontal asymptote here, and my graph will approach that asymptote. So I'm going to take my snaky shape, I'm going to extend it out, and it's going to approach the asymptote of y equals 2. So a few things to notice here is, once again, near the origin, this behavior is characterized by 2 over 7x cubed, and near the end, my graph looks more and more like the horizontal line y equals 2. This approach is the exact same as the power analysis we use for polynomials, just in a little bit more extended matter because we now are dealing with two polynomials, one in the numerator, one in the denominator. Let's take a look at one more example here. We have x cubed over 1 plus x cubed, and 1 over x cubed. So we have ourselves three different graphs that are somehow all cubic. We're wondering, what do they look like when they're all sketched on the exact same graph? So first things first is let's think about the actual intersection points of these graphs. So I have 3 different graphs, and therefore I can have all kinds of intersections. Let's say first I'm going to consider the intersection of F and G, which means that I will set these two to be equal to each other and solve for that. Next, I'm going to consider F is equal to H, which means that I am after the intersection point of the first and the last graph. Set the two of them equal to each other and work out the solutions. And then finally, I'm going to set G equal to H. So I'm looking for the intersection of these two graphs, set them equal, and see what the answer is. So take a minute here, pause the video, and work out what the actual intersection points of all the graphs are going to be, and then try to actually produce the graph where they all live on the same plane. Notice once again, we're only interested in that for x greater or equal than 0. So for the intersection points here, if I set f of x to be equal to g of x, what am I going to get here? I'm going to have x cubed equals to x cubed over 1 plus x cubed. What's my next step? Well, I might notice that this is the same as x cubed over 1, and then I can cross multiply across. There's other methods to do it. No method is better than the other. Just be careful that you are not dividing, but rather factoring when need be. So if I cross multiply, what's going to happen? I'm going to have x cubed times 1 plus x cubed is equal to x cubed. If I expand the brackets, I am going to end up canceling a bunch of stuff. I am going to have, as my next step here, the fact that x to the 6th is equal to 0, which will lead me to the eventual solution that x is simply just 0. Okay, next up I have f of x is equal to h of x. So I need to set f of x, which is x cubed, equal to h of x, which is 1 over x cubed. And again, I can think of the left-hand side as being over 1, and then I can simply cross-multiply these things. So I'm going to get x to the 6th is equal to 1, which produces the solutions that x is plus or minus 1. Excellent. And then finally, the last one, g of x is equal to h of x. So x cubed divided by 1 plus x cubed is equal to 1 over x cubed. Here I already have two fractions. I can cross multiply them. I see that what I'm going to get is x to the 6th is equal to 1 plus x cubed. And now I'm sort of in trouble because even if I move everything over to one side, it's not obvious how to solve this. X to the 6th minus x cubed minus 1 is equal to 0. There's a couple of ways to actually do it. This might be something that you ponder about. It's an equation that you probably have actually seen before. It's just a little bit disguised. This is actually a quadratic equation, except for your x is x cubed. So if I rewrite everything in terms of x cubed, here, I notice that what I do have is a quadratic equation, but for the new term. Something squared minus that something minus 1 is equal to 0. Try to actually solve this as a quadratic equation, potentially with the help of the pre-calculus review package, because these types of things are good to have in your toolbox. Okay, now that I have all of that, let's try to put everything together onto a graph. Let me just move these things a little bit out of the way so that we have a little bit more room to work. Now that we have all this, let's try to put everything together on the graph. We have found out where these functions intersect, so we've actually answered the question that was asked, but let's produce the graph for the comprehensive, to sort of fit. Now, we've already answered the question, where do these functions intercept, modulo solving this equation that I leave for you as the bonus. But now let's actually produce a graph just so we can see how these functions interact graphically on the same axes. So we're going to start off with drawing x cubed. That's pretty straightforward, right? This is just a sneaky shape. Notice that once again, I'm only drawing for positive values of x, really. I'm including a little bit of the other quadrants here just for the sake of being able to see where the functions begin and where they end. So this is my x cubed. If you remember, 1 over x to an odd power will have a shape that is like this. And again, because we're only interested in what happens in the first quadrant, I can only draw one of these. This is my 1 over x cubed. So now I've produced x cubed and 1 over x cubed, and their points of intersection, as per our solution here, are plus and minus 1. So that means that this point is actually at 1, and of course the second branch of this will intersect the graph over here at -1. So this seems to check out with our algebra and our geometric illustration. Finally, I need to draw x cubed 1 over x cubed. This is a cubic Hill function. I encourage you to pause here and really think about how it's going to look like on the graph and how it's going to interact, as per previous slide as well. So pause the video and try to really draw this function as it fits onto this graph. Okay, so being the Hill function for small values of x, it's going to look like x cubed, which means that near the origin, it's actually going to look exactly like this function right here. So I'm going to mimic this behavior near the origin, just so that we actually do have two different graphs. I'm going to make it slightly, not exactly on top of each other. Okay, what happens next? For large values of x, it's going to look like x cubed over x cubed, or simply 1. So because this point where the graphs intersect was at 1, 1, I know that eventually my graph here will actually approach the horizontal asymptote that is at 1. So this will be x cubed, 1 plus x cubed. Here, I can say that it looks like x cubed. If you want a little bit more information on how these graphs look, you can always, of course, plug in some other points. So for example, for 1/2, you can plug in a point and figure out which one of these graphs will be higher, just so that your sketch can be more detailed than what I currently have here. But with our power dominating tool so far, this is a pretty detailed picture. Feel free to check it on your Desmos to make sure that the graphs actually look consistent with what we've come up with in our analysis.